In order to aid in the understanding of my work, I would like to briefly explain how the hippocampus exactly stores our memories. So first of all, the hippocampus is part of our temporal lobe and is therefore also part of our limbic system. Its main role is to control different memory and learning mechanisms. These include, but are not solely, but for example, associative, spatial, and episodic memories, as well as its role in the emotional processing of these. Our everyday, contextual, and episodic memories are formed in the dentate gyrus, which is also located in the hippocampus. It is done so with the help of an excitatory input from the entorhinal cortex. These memories are encoded by a sparse population of principal cells, and we call these engrams. These cells are selected based on their current higher excitability state during memory acquisition. Until now, we have known that these cells are selected, so to say, randomly during memory acquisition. But the problem with this is the following. If these cells are truly selected completely randomly, then how come we are able to reactivate these exact same cells during memory recall? We dived deeper into this network and found that these dentate gyrus granule cells are selectively inhibited by a dendrite-targeting somatostatin-positive interneuron population. So, we hypothesized that if a small population of these, here pictured in red, somatostatin-positive interneurons were to be inhibited, then their target granule cells would become more excitable by the entorhinal cortex. So, we tested this via optogenetics, where we inhibited a subpopulation of these interneurons, so the principal cells would become more active during memory acquisition, and with this we formed a certain engram. And the next day, we re-inhibited the exact same subpopulation of interneurons, or we could also say we reactivated the exact same engram, and with this we found that we were able to recall the memory. So now another interesting feature or characteristic of these engram cells is that, as I mentioned, they are selected based on their current higher excitability state. But this excitability state of these engrams remains high even hours after the memory formation has already occurred. So, if a new event happens within a few hours, then the engram for these two different memories will be shared with the previous one. So the exact same cells are responsible for two different memories because the excitability of those same engram cells was still high to begin with. So now, we know that dentate gyrus somatostatin-positive interneurons play a role in engram formation, and we are curious to see whether or not they also play a role in memory allocation, which I would like to remind you, so memory allocation is when two different context-coding engrams for two different memories are shared. So, how efficient and long-lasting is this inhibition of these interneurons upon these principal cells? We hypothesized that a single activity pattern of interneurons is able to strengthen these synaptic weights long enough for them to be able to store the memory for another day. So they will not be just active for minutes or hours, but possibly even after a whole day. And in order to test this experimentally, we injected an inhibitory opsin containing or a control virus bilaterally into the dentate gyrus of the mice. With this, we selectively made only the dentate gyrus somatostatin-positive interneurons light sensitive. So we then implanted two optic fibers over the exact same area, and via this light, so if we illuminate this dentate gyrus area where we injected the virus, then these somatostatin-positive interneurons will be inhibited upon light activation. So for this, we placed these mice after we handled them into a context A, where they received light illumination for 10 minutes. So we inhibited the dentate gyrus somatostatin-positive cells during this time, but as I mentioned, only in the EOPN3 opsin-containing group and not in the control group. Then we place these mice, so first of all, as I mentioned, so we have the control and the EOPN3 group, and the difference between these two groups is that the control group formed a completely random engram for this environment, whereas the EOPN3 opsin-containing group used those cells that we ourselves were able to select via optogenetic light inhibition. So now the next day, we placed these mice into a completely different environment where they received no light inhibition, but they received 4 aversive foot shocks. With this, once again, we hypothesized that the control group created a completely random engram for this random environment, whereas the EOPN3 containing group used the exact same engram or the exact same subpopulation of cells that we ourselves selected 1 day beforehand via light inhibition. To test these theories, we placed these mice into 3 consecutively different environments. So first of all, we placed them into context C, which is once again a completely novel environment, and as a control, we detected their generalized fear and found that both the control group and the EOPN3 containing group displayed similar low generalized fear. So there was no difference because it was a new environment. But then, interestingly enough, we placed these mice back into context A, which, as you might remember, was the context in which we illuminated the dentate gyrus of the mice. And interestingly enough, you can see that the EOPN3 opsin-containing group displayed significantly higher freezing behavior than the control group, even though they have technically never experienced a fearful event in this environment before. As a control, we placed these mice back into context B, which was the context in which they received the aversive foot shocks. And as you can see here, both mice groups were able to remember the original fearful environment, indicating that their original contextual fear memory was not destroyed for any of the groups. So now, these results indicate that dentate gyrus somatostatin-positive cells have the ability to pre-sensitize a network a day before a fearful event without actually disrupting the original fearful memory, and can cause memory allocation between 2 different contexts on 2 different days. So now, as a summary, I would like to conclude that the inactivity pattern of these dentate gyrus somatostatin-positive cells is first of all sufficient enough to recall a memory itself. But the inhibition of these dentate gyrus somatostatin-positive cells can actually, as I said, pre-sensitize a network a day before a fearful event, and can therefore cause false memory allocation between 2 different contexts. Misregulation of this mechanism may have significance in anxiety-related disorders. So, the importance of this research lies within the fact that we are able to understand how 2 completely different events linked close together in time can create 1 memory. So, our results are expected to contribute to a better understanding of memory processes, and in the case of its malfunction, to a better understanding of the treatments for these memory disorders. Thank you very much for your attention.
Thank you. Thank you, Réka, for this very, very interesting and very high-level talk. Now we would like to give you the certificate, please.